To write a programming language, we're going to need a CLI, like a CLI tool that will run it. And we're also going to need a REPL so that we can run our commands one by one and analyze what results they give. Thank you. But today I'm going to leave those as an exercise to the reader. They're pretty obvious to do, I think. So we're going to use Mocha and some good old TDD to demonstrate how it's all done. So first of all, we need to implement a parser. So we can write some sort of recursive descent parser, which is a parser that uses recursion to create statements and expressions inside the expressions. Acorn and Uglify.js have parsers that are recursive descent parsers. Or you can use pegjs or a variation of Lex and yace, which are age-old tools, to generate a parser for you. And our language is so basic that we can write a parser without any recursion. So I already have the commit here. So we have parse.js, which is basically splits the program, trim the lines and split them. And then for each instruction, we're going to remove comments here, and we're going to remove empty lines, and we're going to turn them into a no-op operation. And we're going to be mapping arguments, and if they are words, then we turn them into words. If they are numbers, we convert them to numbers. And basically, we return an instruction and then split the arguments onto it. So this is going to be a list of lists in which the list is the program, and the lists inside that list are each instruction. So we can look at the tests. So we parse an example program here. So I'm going to add it in. Typing with one hand sucks. And this is the program. This is a comment, and this is line 1. Lines start with a 1. Here we have a go to 3, which will print x, well, no, 1, 2, which will set x to 10 and then print it. And this is what the parse program looks like. It's a list of lists. This is the comment, got turned into an op. The go to instruction, set instruction, print instruction, and then it gets an end added to it so that we know that the program ends back in the virtual machine. So this is going to be a toy language. Your language is probably going to be a lot more complex than this. It's going to feature functions and maybe stack traces when an exception is raised. It's going to feature exceptions probably. And usually we have a separate tokenization and parsing steps. So the tokenization is going to replace, turn your program into a stream of tokens. So the token function, the token which is the name of the function, a paren, and etc. Those are all tokens. And then you have the parsing step that takes the token list and turns it into an abstract syntax tree or directly into your bytecode. And you would usually keep the line number and column number around so you can generate stack traces and errors. So let's start writing the VM. The VM is going to be a function that's going to take this list that we parsed, and then it's going to execute it. And then we're going to create a function that will map the array and execute one by one. Each instruction, which is going to be a function, can modify the virtual machine's state. And the virtual machine state is what variables exist and what values they are, and what's the current line number that's being executed, which is called the PC, program counter. And yeah, so let's look at it. So here's the step function. It's going to execute a single instruction. So as you can see here, this is the exact structure that was the instruction. It's the instruction name and the arguments. And it also takes the virtual machine state. So it goes into this instructions object and gets the instruction, which is going to be print, set, go to, etc. And then it calls it. So basically, our NOP function is really easy, does nothing. Go to just changes the current PC into target -1 because lines are -1 based, but also -1 because the next line after you call step is going to be PC++, so you want to counteract that. Set just sets a variable to a name, to a value, and print just prints it. State is going to contain a print object because when we are testing, we don't want console logs to go out every step of the way. So these are the instructions. Go to 1 makes the state PC -1, which then gets increased to 0. Set is going to set the variables. Here's the state, which contains the variable a to 0. And we're going to set a to 10. We're going to make sure that a is 10. Print is like pass the state with a print function and then make sure that the printed value is what we expect. So we're going to print an a, which is going to print 42 because a is 42. And we resolve variables. And the way we resolve variables is we have a function called toConstant that takes the state and it takes the variable or value. So print is going to either take a variable name like A, B, or C, or it's going to take a literal value like 42 or 10. So if it's a constant, then just return the constant. And if it's a variable, then return the variable. Of course, we have an assertion to make sure that the variable is there. Otherwise, we generate an error, unknown variable, whatever. So on to the next commit. So here I'm just adding some instructions. So incur by is the plus equal operator. It's going to increase a variable by a certain amount. Less than or go to is our first conditional operation, which is if our variable is less than another variable, then go to the next line, we're cool. Otherwise, go to this other line that I said. And this is how we're going to have our conditions. So here's our tests. Because A is less than B, then the PC stays at 1. And if A was 44, then the PC would be 98, because it's that go-to again. So if the go-to line is 100, then you need to reduce 1 because lines are 1 based. And then you need to reduce 1 because state.pc is going to get incremented next. So we're going to create the function that calls the function that we just created. The function we just created is all right, it's all good and fine, but it only executes one instruction. So we're going to create the function that executes the entire program, and this function is obviously going to be using the function that I just showed you. Oops. So we still have all the instructions, and we still have the step function, but now we have a run function. So we have a little guard over here. If the program is a string, then we're going to parse the program first. This allows people to just pass strings to the run function that aren't parsed yet. So it's going to create the state PC, which is going to be 0. The first line that's executed in any language is the first line. We're going to create the variables objects, and we're going to create the print function, which is just going to be console log. So this is very, very simple. We create an instruction, and while that instruction is not end, we're going to call step, which is going to execute one instruction, and we're going to increment the PC. And this is why goto always has to do -1, because of this PC++. So now for the tracing JIT part, because we now have a VM that's capable of executing an application. So there's some theory here. So what's a tracing JIT? Tracing JIT basically is going to take your program while it's executing, and it's going to take a trace, which is a series of instructions that are being executed, and it's going to take that trace, which is basically just a line of instructions, which is this linear sequence of frequently executed operations. So how do we do this? So what Mozilla did, and I have on the slides there's a link for their article, which explains how they implemented their tracing monkey, I don't know, their monkey. So you have 3 states. The first one is monitoring. So you're monitoring to try and see when a trace starts. And when you're monitoring and there's a goto or any kind of jump like return of a function or a while loop or something that goes backwards, if you're jumping backwards, then this must mean that there's some sort of loop going on. So you're going to a certain PC, and that PC is going to be cold or hot. So you're going to have you're going to be keeping account of how many times the PC is going to be executed. So if it's below a certain threshold, we say it's cold. And if it's cold, we keep monitoring, and we just increment the counter. So we say we went to PC number 0 3 times, and now that we came to PC 0 again on a backwards jump, we say it's 4. But when that number of times that the PC is being executed reaches a certain threshold, we say that it's hot. So at first, there's not going to be a trace. So we're going to hit our hot PC without a trace, and we go to recording mode. So in recording mode, we're still executing the program, but we're keeping track of what's being executed. So this is when this is a Mozilla-specific thing. When you call a function that calls JavaScript again, and it's hot, we're not going to need this one. So what can happen in recording? In recording, we can abort because the trace that we're trying to fill, the array we're trying to fill is too long. We abort. Or we say we closed the loop when the trace got back to where it started. So when you're keeping a trace, the trace started on line 1 because there was a goto on line 3 to line 1, and you execute, and then you say it's closed the loop when you find another goto to line 1. So when you close the loop, you go to monitoring, low disk space, interesting. You go to monitoring, and then you go to executing because you hit a hot PC. Because the PC has a trace now, because you closed the loop, you created a trace. And when you create a trace, you go to execution mode, which is where you convert your trace to machine code or to something that's a lot faster than your language, and you execute that. So when you're executing, you can execute, you can exit, and you go back to monitoring. Here we're not going to go to recording again. So in executing, you exit when one of the conditions that were happening during the trace were not, is not true anymore. So what does this look like? So here we have our fake language. It says go to 3, so it's going to have a go to backwards, and 3 is going to be eventually a hot PC, because go to 3 is going to be executed a bunch of times. And after that, you go to recording and you record the trace. And the trace is going to look like this. On line 4, there will be a guard. So PC is going to be 7 if n is not greater than 0, because we have that if go to 7 if n is not greater than 0. When we were tracing, by the way, we were recording the results of conditional operations, and this is why we create the guard, because the condition was met, and we make sure the condition is still met. And then we do n minus minus, and then loop back to 4. And then when we exit from the guard, PC becomes 7, because that's what the guard said, because go to was go to 7, and we go to the end. So how do we implement this kind of stuff? A modes at a time. So we start with monitoring mode, which again is we wait for a backwards jump to detect the loop, and we increment a hot counter. And we say if this PC is hot, then we're going to go to recording mode or execution mode. All right. So here we are. So the step function is a bit different. So we're going to make, we're going to have an isJIT Boolean signaling that the VM that we're running is a JIT. And if the tracing mode is recording, so this is kind of a state machine, and the instruction is a jump, and if the jump destination is below states.pc, which is, this is a backwards jump, then we're going to process this backwards jump, which is going to be, we have a PC temperature for all the PCs, and the jump destination is going to be incremented by 1. And if we're above the hot PC threshold, which is just 10, then if there's a trace to execute, then we're going to execute it. Otherwise, we're going to go to recording mode, and we're going to reset the JIT state, which is going to be set PC temperatures all to 0 so that nothing is hot again, and go to recording mode. So now for recording mode. Monitoring mode was just trying to keep, trying to look at backwards jumps and seeing if the PC was hot. In recording mode, we're going to passively record what's being executed, except for non-conditional jumps. So go-to statements, we don't record them because they are not relevant when you go to execution mode. It's just a bump in the road for the trace. And that's part of the reason why tracing JIT is a lot faster than another kind of JIT. So if we go over 100 steps, we're going to abort because the trace is too big. We don't want to waste a lot of memory. If we see a conditional jump, which is this, this if something is less than another something, then that's going to happen. We record a guard. And the guard is going to be what's going to ensure that the condition is the same when we execute. So if we get back to the beginning of the trace, we say we've closed the loop, save the trace, and go to monitoring mode. And in monitoring mode, it's going to pick up that trace and it's going to execute it immediately. So hopefully with enough disk space. Where are the changes? So here's the function. So inside step, which is the function of what we wrote a long time ago, we're going to see if the state is not monitoring, if it's recording, then we're going to record. And we're going to have a record start PC, which is when we started recording, what was the PC? So when do we close the loop? We close the loop when we reach this PC again. So this is closing the loop. We compile the trace, and then we reset the JIT state. So this is when we will abort. If it's over 100, it's too much memory, we quit. If the instruction is no up or go to, we return. We don't care about these. If the instruction is less than our go to, which is our conditional jump instruction, we record what the result was. So we turn into a constant the first argument. If it's greater than the second, then it does jump. So we push a guard instruction, which is the first argument, second argument. Does it jump? And if it does jump, then it's going to be the state PC. Otherwise, it's going to be the go-to argument. So this is the guard. It's kind of the most complex thing we have. And this is compiling the trace. Okay, this is not compiling the trace yet. So the way we're going to compile the trace is going to be a bit fun. So first we're going to refactor a bit. We're going to make the file a bit smaller. So we create a compilation.js file where we add the has trace, compile trace, and execute trace functions. And the VM function now starts requiring the file. So that's it. So way back in the day, there was a compiler called TCC. It's also a library, so you can include it in your C applications. So it's called the TCC because it's tiny C compiler. It also has a CLI, so it compiles and runs C if you give it the -run flag. So you could have some sort of C script in which you have on the top the shebang user bin tcc-run, and it would create an executable C file, so you wouldn't have to compile it and then execute it. So now we're going to do execution mode. So the reason I told you about TCC is because we're going to use TCC. I've installed a library that's called I forget. That's called Stream TCC Goodness that enables you to use TCC. But because the library sucks, I'm not going to use it. The library is going to be useful because when it's installed, it has a post-install hook that installs TCC, and that's the reason it's here. It's hard to compile stuff, guys. So this is our compilation.js file. This is where we compile the things. So we're going to compile programs to int main, find the variable declarations that are in the state and put them in here, make them a loop. It's going to be a loop. The trace is a loop. We put in the program, and feedback is when we print the state of the program so that we can read it from Node.js. And we're going to return 42 because why not? So this is how you compile every variable, every instruction. So a set instruction is just A equals B, whatever it is. Print is printf. You printf %d and a new line, and you put in the variable or the value. You could also print values, but C doesn't care if it's a variable or value because they're interchangeable. Increby is just plus equal, and guard is the complex cousin, which is if this is still greater than, if it's different from what we had and it does jump, then PC equals target PC and break. And then when we break from the loop is when we go to the feedback part. And the feedback part is going to be printf, the variables, with var name equals value. We join it with an %. And yeah, that's basically it. We print the variables, including the PC. And then we go back to Node.js because we've executed the program and we can run it. So where's exec? Yeah, so exec trace, that was a to-do before, compiles the trace to C. So, and then it spawns the program with spawn sync with the dash run and the dash argument so that it runs the standard input. The input is going to be the C program, including in UTF-8. We make sure the status is 42 because there could be an exit condition from the compiler, which is not 42. And then we read the last line. We take the PC and the variables, and we put them in the state. And that's it. So if we go into test compilation, these are some programs that we're running. Compiles traces to C. This is an example C program. Int main, int PC equals 42, A equals 1, B equals 1. This is the reporting. This is when we report back to the Node.js program. And this is execution. So this is executing the trace, and we make sure that standard out is going to be the numbers that it's printing here in this nice loop. And then we make sure that the variable I is now 11, so we reported the variables back and it's now 11. So this program here is counting to 5 million, and it counted to 5 million in a very fast time. So before we were executing this step in 3.8 seconds. Now we don't go over the time. We barely see the test stopping there. So this is the power of the tracing JIT. It's just executing the thing in no time at all. So this is the end.